This part of the earthquakes chapter is about the secondary effects of earthquakes and also the methods that scientists use for forecasting earthquakes. The primary impacts from earthquakes are the shakes, the shaking, the surface waves, and the body waves. But there are secondary effects like liquefaction and tsunamis that can be way more deadly in destruction than the shaking of the earthquake itself. And you can see what some of those are. Ground displacement and ground cracks, liquefaction and subsidence, sand blows and mud volcanoes, landslides and mudslides, fire is always a biggie, tsunamis, seiche waves, and disease. So this happens to be a ground crack, and you see it's a pretty big crack in the earth. This happened along the Denali Fault, which is in Alaska, and there was a 7.9 magnitude earthquake. That's a pretty high magnitude earthquake that happened in November of 2002. This is one of those scenarios where you can have a high magnitude earthquake, but you don't have a lot of damage to structures, so you would have a low Mercalli intensity. And the reason for that is because there's nothing here. You don't see any highways, you don't see any buildings, you don't see any shopping centers or bridges, skyscrapers, not here. So high magnitude, but low Mercalli intensity. The one thing that was in the line of fire for this earthquake was the Alaska pipeline, the oil pipeline. But it turns out that there had been this brilliant seismologist at UC Berkeley that had done the design on that, and he put some safeguards into it, and it turned out that it held up just fine. Then this is some ground movement. From the 1992 Landers earthquake. That's down in Southern California in the desert. The magnitude was a 7.3, another high magnitude quake here. This was the first time that seismologists found out that earthquakes don't just rupture one single fault line. There were 5 separate fault lines that ruptured during this earthquake. Same thing happened with Pine Crest earthquake, or sorry, the Ridge Crest earthquake that happened in 2019. Then this, of course, is the famous fence at Point Reyes that moved, that had an offset of 16 to 20 feet in it. Then there's liquefaction and subsidence. Liquefaction is when the ground loses all its strength. And it basically turns to liquid. That's where we get the term liquefaction. Anything then that is built on that surface is going to be destroyed or heavily damaged because the support is gone. This is a picture from the Good Friday, Alaska earthquake that happened in 1964. It was a 9.2 earthquake. That's the highest magnitude earthquake to ever hit North America. There were roads, there were rail lines destroyed, there were children swallowed whole during this earthquake by fissures that opened up in the ground. In some cases in this earthquake, the ground was raised as high as 30 feet, and the shaking in this earthquake lasted for 4 minutes and 38 seconds. That must have seemed like a lifetime. If you've ever been in an earthquake, you know that if it just shakes for 5 seconds, it feels like a lifetime. So shaking for 4 minutes and 38 seconds is kind of just unbelievable. 600 miles of fault line ruptured all at once. So Turnagain Heights was a bluff that overlooked Turnagain Bay, which is an arm of the Pacific Ocean. This bluff was not solid rock. It consisted of sand, silt, and clay, not a consolidated rock in sight here. So this type of material, when it's shaken, can liquefy. You don't want to build on unconsolidated ground in earthquake country because liquefaction is always a major concern. So it liquefied and it collapsed. The water molecules that are adding support to the particles, give them a good shake and they are displaced too. So that support is lost. So everything just starts caving in. Not a good place to build on at all. Here's another view. You see what happened to these homes. You see what happened to the ground. There's another view of it, just the total upheaval and collapse of everything. Well, you would think that people would learn their lesson, right? Okay, it happened once, it's going to happen again. But we as humans, as time goes by, we forget things. And it's no different at Turnagain Heights. People bought property up there. They built back bigger and better than ever. There's absolutely nothing about the geologic situation that has changed. You still have the Aleutian Trench offshore. You still have the possibility for a megathrust earthquake. Remember, these are the most destructive because they're associated with subduction zones, and the stresses that build up along these faults are capable of producing these 8 and 9+ earthquakes. So nothing has changed about the situation. And in fact, just a year or so ago, there was a major earthquake that hit in Anchorage, but no damage to the extent that the 1964 did. There were some roads that were mangled and some buildings that were destroyed, but I never heard anything about liquefaction taking place in Turnagain Heights. This is in Japan. This was a 1964 earthquake. These buildings collapsed because the soil underneath liquefied. And it's pretty ironic because these buildings had been built to a certain earthquake code. But whoever built them forgot that what you build your structures on is just as important as how you build your structure. Somebody forgot that rule. Here's another view of Japan. It's kind of surreal to see buildings just leaning over like that. It's like they're defying gravity almost. So this was the profile, the soil profile at Turnagain Heights. Again, you see sand and gravel, clay, silt, no solid rock in here at all. So give that a shake. It's like a mud milkshake at that point, and that everything collapses then. And if you've built anything on top of it, then it's going to collapse too. Landslides and mud flows can occur. Landslides and mud flows are going to be common on steep slopes anyway. They're hazardous anyway. Let's throw an earthquake in. These steep slopes are going to be prone to moving. We shake them, we vibrate them, and then they're going to fail. This was in Central America. It was a mud flow that was about 15 feet high, and what you're looking at there are roofs of homes. These are landslides that happened in an earthquake that occurred in the area of Kashmir, this area between Pakistan and India. Those landslides weren't there before. If you look up here, you see some green pasture land, and you see that it is now down here. These landslides have also dammed the river, so that could potentially cause flooding and other problems. Then we have tsunamis. Tsunamis are seismic sea waves. They're not tidal waves, as you hear some people refer to them. Tidal wave is something totally different. A tsunami is produced anytime the ocean floor is displaced. And that can certainly be with an earthquake, but it can also be from volcanic activity or from undersea landslides. But it's any event that will cause the seafloor to move. Well, think of this. We have an ocean above that seafloor. So if the seafloor is moving up or a portion of it moving down, then that means that there's going to be a drop and a rising of the water. So there's this, it's like dropping a pebble in the middle of a pond. There are these energy waves that are going to emanate from that movement, from the epicenter of the fault, if it's a fault that we're talking about. And that water is going to start moving out at a phenomenal speed at about 600 miles per hour. That's about the speed of a jetliner. These things aren't noticeable in open ocean because the energy goes all into, we've talked about wavelength before. Let's get a pen here and do this. So we have these energy waves, and in open ocean, the energy is here. The energy is in the wavelength, the height between, or the distance between each wave crest. But when the wave makes it to the shore, the bottom of the wave will begin to feel friction with the beach. Let's put a beach in here. Friction with the beach, so the bottom part slows down, which allows the top part to get higher. So what might arrive at the shore, where beachgoers are enjoying themselves, is something like this. And then the slowdown of this wave can allow the others to catch up to it, so you can have the wave even higher than it normally would be as another wave is superimposed on it. And the run-ups, the distance inland that these things can reach, can be up to about 100 feet, or in the case of the Tohoku earthquake, I think the waves went inland for about 6 miles. So the first sign of an approaching tsunami, if you're lucky, will be the draining of the coastal area. It's like the water is flowing back out to sea. So you might see rocks that are exposed, that were never exposed before. You might see fish that are flopping around. That is your signal to get out of there as fast as you can, because what will follow, what happened, it's just the trough of the wave has arrived. The trough of the wave has arrived before the crest of the wave has. You might have 5 minutes, you might have 30 minutes, but the crest is coming. And there are multiple crests that are possible. A lot of people are killed because they hear about what's going on, they go down to the water to see for themselves what's happening, and then they get killed, they get drowned by a second, a third, or even a fourth wave that might come in. So it's not just one wave. So this shows us what's happening here. Here's movement along the sea floor. Right there. So this part of the water is going to be pushed up. This part where the fault dropped is going to be pushed down. It's like a hole in the ocean. How long do you think you can have a hole in water? Have you ever poked your fist into a pail of water? The water immediately moves in to fill up any low area. So that's the energy, that's the start, that's the initiation of the wave. A seiche wave is this swaying of water, this back and forth motion of water that will happen in an enclosed body of water, like a swimming pool. I've heard students tell me that during an earthquake, they looked out and water was sloshing out of the swimming pool. It could be a lagoon, it could be a pond or a lake. That's one of the worries with Lake Tahoe. There are faults at the bottom of Lake Tahoe. So if we end up with a seiche wave, a lot of those resort areas around Lake Tahoe could be destroyed. A lot of life could be lost if people weren't aware that the seiche wave was happening or imminent. So some notable tsunamis: 1964, Crescent City, California. Crescent City, if you wanted a tsunami capital of the lower 48 states, it would be Crescent City, California. There was a major tsunami that happened there as a result of the earthquake in Alaska in 1964, the 9.2 earthquake. The 2004 Indian Ocean tsunami, that was a 9.0 to a 9.3 earthquake. And the 2011 Tohoku earthquake in Japan, which was a 9.1. This is 1946. This is in Alaska. And you see a lighthouse standing there proudly before a tsunami hit. This is what it looked like after the tsunami hit. This is 1946 in Hawaii. Again, Hawaii is quite prone to tsunamis because think about it, it's right out there in the middle of the Pacific Ocean, surrounded on all sides by subduction zones. So anytime there's one of these megathrust earthquakes and a tsunami happens as a result, then Hawaii can get pounded by them. But this is what you're seeing that you don't want to see. These people have gone back down to the beach because they're collecting fish. This is the trough of the wave that has arrived. What's coming is the crest of the wave. This is Indonesia, and you see just the power of these things is just unreal. Some people say, oh, I could outswim a tsunami. You might be a strong swimmer, but you're not going to be able to survive all the junk that these tsunamis are carrying. There could be cars, there could be homes, there could be tin, all manner of things. And you see the fish and the fish that got stranded as the wave moved back to the ocean. This is in Hilo, Hawaii in 1960, and you see just the power of these things. These are parking meters. Parking meters are pretty darn strong, but the power of that water just bent them horizontal. There were 61 people that were killed in this tsunami. Most of them died because they went down to the ocean. They went down to the shore to see what was going on. And then this is the infamous 2004 Indian Ocean tsunami that resulted from the earthquake, the 9.0 to 9.3 earthquake that happened in Indonesia here. That tsunami spread out across the Indian Ocean. There wasn't any place around the Indian Ocean that wasn't impacted, and there were about 230,000 people that were killed. The Indian Ocean did not have a tsunami warning system at the time. The reason that they didn't is because there had never really been, I mean, there have been some isolated tsunamis with people killed, but they certainly weren't as common here as they would have been over in the Pacific Ocean. The Pacific Ocean does have a tsunami warning system. The Indian Ocean has a warning system now. This was part of a little community in Indonesia, near Banda Aceh, where the epicenter of the quake was. This was a satellite view of the area before the tsunami hit. This is what it looked like after the tsunami hit. This is another view of some of the damage from it. I misspoke there. This is damage from the Tohoku earthquake. And this is Crescent City. Crescent City, you see how it got its name there, but the underwater geography just makes this area really susceptible to tsunamis. The configuration, there's a seamount offshore, and it seems like the energy just like makes a beeline toward Crescent City. That doesn't mean that other areas along the California coast are not in danger from tsunamis, because they can be. And I should have mentioned that in this 1964 tsunami, there were 14 people that were killed here in the fourth wave that hit the city. It wiped out the downtown area. There were fires because oil tanks were colliding with each other. Fires broke out. And this is the 2011 Tohoku earthquake. Crescent City received damages from that. The harbor was suffered severe damage, as well as the Santa Cruz harbor. These are some of the boats that have crashed into each other. Then there are sand blows and mud volcanoes. These are related again to these waves that are moving through, shaking the soil. Sometimes the water molecules become pressurized and they blow out of the ground, and they bring sand or mud with them. That's what we're looking at. That's a mud volcano. And these are sand blows. These are farm fields in Watsonville. This happened during the 1989 Loma Prieta earthquake. So those fields are basically ruined because all of that sand is covering these crops. Then fire is another major hazard that we have to deal with in earthquakes. Think about all the things that we are carried in pipelines underground. Some things we don't even know about. But a lot of flammable material like gases, liquefied natural gas or natural gas. And all it takes is an electrical line coming down. These pipes are going to get broken so that gas starts leaking into the air, and there's a spark, so a fire. Or think about all the wiring in buildings that can be damaged. So we know about the 1906 earthquake and the fact that San Francisco was very heavily damaged by the fire that went through the city, and they had to set fires to save the parts of the city that weren't burning. Here's some views of that. These are people on Nob Hill that decided to have a picnic and watch the downtown area burn, and that wasn't a good idea because it was shortly after that Nob Hill started burning too as the wind shifted. This is Kobe, Japan, 1995, of a fairly famous earthquake that occurred here that destroyed totally parts of Kobe. And then, of course, the Marina District in 1989 suffered heavily, and a lot of the water lines broke, and there was no way to get fire to them until they put these fire boats out into the bay, and they were able to get water in to try to put out these fires. Then there can also be sicknesses. That was realized after the Northridge earthquake. After the Northridge earthquake, several months after the earthquake occurred, there were all these people that were flooding into the emergency rooms with, they felt like they had a bad case of the flu, they were coughing, they had fevers. It turned out that they had valley fever. Valley fever is not unknown. It happens in the Central Valley, and it usually impacts farmers because farmers are out tilling the soil. It's always dusty. They're breathing this in, and the organism that causes valley fever lives in the soil. So what happened after the Northridge earthquake, there were all these landslides because you have these steep slopes, unconsolidated soil. They got vibrated. The soil was released into the air, and because there was a weather system called a temperature inversion, that dust couldn't dissipate. So people were breathing it in for several days. Between January 24th and March 15th, 203 cases of valley fever were reported in Ventura County, compared to 60 cases for all of 1993. So it was at that point that doctors realized that they had a situation on their hands, and they started looking into it, and they started looking at pictures of this dust that was in the air, and they realized that this is how everybody was contracting the disease. Well, some significant earthquakes, just want to point out a few things here, like the Northridge quake. There were 66 people that were killed in the Northridge quake, and it was a 6.8. The damages, the Mercalli intensity was from a 7 to a 9. The Loma Prieta earthquake was a 7.0. There were 67 people killed. And if we look down here at, let me find it, let's see, oh, here it is right in front of me, Armenia, Turkey. That was a 6.8 earthquake too, same as the Northridge, but look how many people died. This is a result of this area being fairly poor. The homes were built of adobe, which is dried mud. So you vibrate those and they're going to be broken. Any structures like high rises or apartment buildings built with unreinforced concrete. So you had that many people die compared to the same magnitude in Northridge. So just a result of, you know, economics. Mexico City. This one is an interesting one. We talked about this a little bit earlier. It happened in 1985. The epicenter of that earthquake was about over 200 miles away from Mexico City. 8.1, yeah, that's a big earthquake, but 200 some miles away, you wouldn't expect to get 7,000 people killed. This is where you had those buildings that went through resonance and they were collapsing. 7,000 could be a low number. And then look at the Mercalli intensity. New Madrid, Missouri. This is one that's not on a fault line, or sorry, not on a plate boundary. It's on a fault line, just not on a plate boundary. We'll talk a little bit more about that. So there are over 380 major cities that lie on or near unstable areas of the Earth's crust. These are all these red dots, all these red lines indicate earthquakes. Look at these. Just that's the Mediterranean Himalayan belt. This, of course, is the Circum-Pacific Belt. If we're talking about volcanoes, we call this the Pacific Ring of Fire, but if we're dealing with earthquakes, it's the Circum-Pacific Belt. There's Hawaii right there. So they're fair game for any movement that occurs along the Pacific Rim. And then these are the mid-ocean ridges here. Oops, that's not the mid-ocean ridge. That is in Africa. Here are the mid-ocean ridges here. So these are fairly shallow earthquakes, and nobody lives on the bottom of the ocean, except maybe SpongeBob. But you do have lots of infrastructure down here, like cables for communications, for monitoring earthquakes. So sometimes those are damaged. So earthquake-prone areas. Where would you not want to live if you were earthquake phobic? Dun, 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 dun. Japan. 15% of all earthquake energy worldwide is unleashed on Japan every year. Since 1900, how many magnitude 8 earthquakes have we experienced here in California? Maybe one, the 1906 San Francisco earthquake. Since 1900, how many magnitude 8 earthquakes has Japan experienced? About 27. So quite a difference there. Well, where else would you not want to live? Mexico, South America, Central America, Western North America, Oregon, Washington, Alaska, certainly. We're running out of places. So if you live at an intraplate location, are you guaranteed not to experience an earthquake? Well, we might say, yeah, sounds likely, but that's not the case either. New Madrid, Missouri. It's in the middle of the North America continent. 1811, 1812. 3 large earthquakes, thought to be as big as 8.5. The Mississippi River ran backwards. Reelfoot Lake in Tennessee was created at the time. This area now has 12 million or more people living in it. Cities like Memphis, Nashville, even Chicago, as far north as Chicago, St. Louis. These are all areas that could be damaged, and I would say 99% of the people that live there have no idea that they're living near a fault line. There's the town that was destroyed in 1811, 1812, but it was just a frontier town at that point. This is in the foreground here is a levee, and the Mississippi River is on the other side of the levee. That's the museum. That's the New Madrid Museum. And then this is the earthquake hazard map. So some things here you should be able to know the relationships. Why are these areas, why do we have the highest hazard in these red zones? Well, here's the San Andreas Fault. This is that Walker seismic belt. Here's the Cascadia subduction zone up here. And then here we have the activity associated with the Yellowstone. And here is the New Madrid area. And of course, here's the Aleutian Trench here. And here is Hawaii here. Just remember that the earthquake hazards, let me get this pen working, the earthquake hazards here are related to the magma that's coming up under Hawaii, the big island of Hawaii. And then this map was produced in 2016. USGS had to go, United States Geological Survey, had to go and revise the chances of damage in different areas because of the number of earthquakes that were happening in Texas and Oklahoma from fracking. Traditionally, I shouldn't say traditionally, I should use another word. For most of the history of Oklahoma, they have had earthquakes, but they haven't been high magnitude. We talked about this earlier. From the mid-2000s, like 900 earthquakes occurring in Oklahoma. So USGS, as a result of these earthquakes, had to go ahead and amend some of their hazard maps that they publish. Then this is the Walker seismic belt right here, right through here. This zone of seismic activity, that the new thinking is that if there is a new divergent plate boundary that's going to happen, rather than everybody thinking, oh, well, this part of California is going to break away, there'll be a little sliver of California that over time will break, I can't draw that properly, but will break away from the rest of California, and it will be moved on up to the Aleutian Trench, where two things could happen. Either it gets subducted into the trench, or maybe it's too much granite here and it plugs up the trench. Well, that was the old way of thinking. The new way of thinking is that this area, because it's being stretched, remember when you stretch crust, it thins out, so it's going to be very weak. So this area of stretching down here in the Gulf of California is extending up through here. So that might be where the breakage occurs. That's the new California and Nevada tectonic story. So oceanfront property in Winnemucca. So geologists come up, seismologists come up with these hazard maps. So the latest hazard map shows that there's more than a 99% probability in the next 30 years for one or more 6.7 magnitude earthquakes. That's by calculating all of the probabilities along all portions of the fault lines. And there's a 46% chance of 7.5 or greater magnitude over the next 30 years. We hear San Andreas, but really the most dangerous fault in the Bay Area is the Hayward Fault. It has a higher percentage of probability of an earthquake happening than the sections of the San Andreas Fault in the Bay Area. So here are our plate boundaries. So we're talking about movement along plate boundaries. This is a subduction zone. What seismologists have found out is there are different zones of earthquakes as the ocean plate is moving, in this case, underneath another ocean plate. There are shallow focus earthquakes, there are intermediate focus earthquakes, and there are deep foci earthquakes. This is called the Wadati-Benioff zone for the two seismologists that discovered that these earthquakes do occur in these clusters. But what I want you to pay attention to is look at the angle of subduction here. The angle of subduction means, like, this is Japan. So this is the Japan Trench, and you see where these clusters of earthquakes occur. So there are earthquakes that can occur in China, as far away as China, as a result of how this plate, the angle that this plate is subducting at. So that is, I would say, not so steep, but if it were a fairly level area of subduction, it might be, I'm not drawing that right, it might be even more inland of China where these earthquakes could occur as a result of the megathrust quakes that are happening out here, and as a result of the plate diving underneath the other ocean plate. So the Wadati-Benioff zone. Can we predict earthquakes? It would be great if we could, but we cannot predict earthquakes. We're not that good. We thought that at one time we might be, but we can't tell you what the magnitude is going to be. We can't tell you the time, can't tell you the place. So forecasting of earthquakes is based on historical occurrences and on the statistical probabilities. That's how we were able to get the 99% probability previously. So it's a 70% chance that the Bay Area will experience a magnitude 6.7 plus between 2000 and 2030. There's a lot of leeway here, isn't there? And we are pretty good at this. And, or not. As an example, Parkfield, California. Parkfield was a place where earthquakes had occurred there regularly on like a 22-year interval, a magnitude 6 earthquakes. 6 of them occurred on the fault, and they were very unusual in their regularity. So why does that happen? I'm going to pass through this and just show you. Here's the San Andreas Fault. This is moving. This part of the bridge is on the Pacific Plate, so you go across the bridge and you're on the North America Plate, and you end up in the tiny, tiny, tiny little town of Parkfield. Parkfield is famous because of the regularity of the earthquakes that occurred there. Earthquake capital of the world, be here when it happens. So the earthquakes happen so regularly there that geologists thought that they could study here what would happen before an earthquake. Maybe there would be some things that happen that would allow prediction of the next earthquake. So they set up shop here, and they put seismometers here, they put creep meters, they put strain meters in place, thinking that there was going to be another earthquake in 1993. So they were ready for it if it happened. Well, it turns out that it did not happen. So they waited and waited and waited, and they had to wait until 2004 before the earthquake, before magnitude 6 earthquake happened. So the thinking is that those earthquakes happen here with regularity because this little area is between right here, Parkfield, is between a locked area of the San Andreas where there haven't been any earthquakes, except 1857, there was one. That was the Fort Tejon earthquake, and a creep zone where the Pacific Plate is creeping past the North America Plate and it's not experiencing any earthquakes. So they thought it might have something to do with that. Well, as a result of the earthquake not happening when they thought it would happen, the NSF, National Science Foundation, along with NASA and the United States Geological Survey, got funding to build what's called the San Andreas Fault Observatory at Depth, or SAFOD. They drilled a hole into the fault, through the fault, and they put all kinds of monitors in here. And it turns out that they actually had monitors in here. They put geophones in here. They put GPS clocks in here to see what was going on, what geochemically in here might be causing the earthquakes on such a regular basis. They thought that they would be able to figure it out. And some of the monitors were in at the time that the earthquake did happen. One of the things that they think might be causing these earthquakes to happen on a regular basis is they encountered this zone of talc. Talc is a mineral that is kind of soft and pliable, kind of greasy, and it's also common in serpentinite, California state rock. So they think that because the fault can slide easily past that smooth rock, that might have something to do with the regularity, but the research continues here. So forecasting seismic gaps, remember that's an area where the fault hasn't moved in a while. That's a red flag. So if an area has a seismic gap, we pretty well know that it's going to move at some point. You always hear about pets, animals being able to predict earthquakes. That has no scientific basis to it. Microquakes can be measured. That might be helpful in forecasting earthquakes. Rocks changing in volume because of slight movements that would be too small for us to feel, but these instruments can pick them up. Changes in water levels, changes in the amount of radon gas, and we have all these water wells and wells to measure different gases at Parkfield. So it remains to be seen, but where we're at now, no predicting. There was no prediction value of anything when the 6.0 earthquake did occur, even though it was like a pincushion there with all the monitors that were in place. So the best we have now is just this forecasting of these probabilities. All right, so that concludes the earthquake chapter. See you next time.